a couple of years after my last visit. So if you can read the writing, and if you can't, I encourage you to move forwards. I promise that I don't have coronavirus. I won't be spitting on you and infecting everyone. I'm going to be talking about axion dark matter detection in an RF cavity. So for those of you who are not familiar with what axions are, I will give an extremely brief introduction. And for those of you who are, I apologize for repeating stuff that you know extremely well. Then I will move on to the second part of this title, which is how axions are planned to be detected, because of course we haven't detected any yet, but we hope to in the future. So exactly what the detection will entail in general, I will have sort of a general discussion before moving on to the specifics of what's new in what we did in December in this paper with the archive link given here, where we proposed a novel strategy that involves using upconversion in a radio frequency cavity, which allows access of very small axion masses. So I'll explain exactly how that works, but let's start first of all with a lightning introduction to axions. Okay, so for those of you who are familiar with non-abelian gauge theories, which is hopefully everybody, you know that there is a term in the Lagrangian that looks like a total derivative, but that due to the non-abelian nature of your gauge theory actually can have physical consequences. And indeed the physical consequence of this is that CP is not a good symmetry of your theory. And so what this tells you is that the neutron should have an electric dipole moment. So the neutron should have an electric dipole moment, and you would expect it to be relatively large. Indeed, the expectation is that the neutron electric dipole moment denoted dn should be something like 10 to the minus 16 times theta bar electron centimeters. But experimental limits on the neutron electric dipole moment tell us that theta bar must be less than or similar to 10 to the minus 10. So this, in essence, is what we know as the strong CP problem, which is why is this a priori order 1 term in our fundamental Lagrangian seemingly so small, and therefore why is CP violation so weak in the strong interactions? And so the solution to this was proposed in the late 70s to introduce a new symmetry. So hopefully everyone is familiar with the idea that if you have a problem, the simplest way to resolve it is you introduce a new symmetry. So indeed that's exactly what people did, and they proposed introducing a new U1 symmetry called the Pichet-Quinn U1 symmetry, which is anomalous under QCD, and therefore it has a term coupling its pseudo-Namu-Goldstone boson to this same combination of the field strength and its dual in QCD. So this means that now your Lagrangian has a term that looks like A, which is the axion field, over its decay constant Fa, plus theta bar, and then times the thing that I wrote above, minus obviously the theta bar. And so the physical consequence of this is that now you have a shift-symmetric pseudo-scalar field, so it's odd under CP, that solves your strong CP problem because the potential for the axion is such that it minimizes when the expectation value of your axion field is roughly, theta bar Fa. And thus solving the strong CP problem because you dynamically relax the theta to 0, and therefore you expect it to be extremely small. So this is where axions originated. And then in sort of the later decades, and indeed this was popularized in the mid-2000s, people found that besides this axion, which we'll call, so this guy is the QCD axion, we also had what we now refer to as axion-like particles, or ALPS for short. So these guys were popularized in the mid to late 2000s by the realization that this was sort of one of the few concrete predictions of known, thus far, string compactifications. And indeed, there's a very famous paper on this by Spectral and Witten in 2006, showing that in typical string compactifications, you not only have one axion, which you would identify as the QCD axion solving the strong CP problem, but you would have a whole plethora of axion-like particles, a combination of which is the one which solves the strong CP problem. So now what you're expecting is many Alps in the landscape of your low-energy theory. So that is one of the motivations for axion-like particles. But another motivation is that there is also a very simple mechanism for obtaining the correct dark matter relic abundance if you have an axion-like particle in your low-energy spectrum. And indeed, this is through what's known as the misalignment mechanism. So that was a further motivation for considering Alps. A third motivation for considering Alps, which is a rather more experimentally motivated one, is that we have technology to look for such states. And if they're already looking for other states that are theoretically well motivated, we should not be prejudiced against things which are perhaps slightly less well theoretically motivated and look for them at the same time.
Is there a restriction on the range of masses for axion?
I'll explain that in just a moment. Yeah. So there are a couple of key differences between the QCD axion. Tell me if this is too low, by the way. And Alps, in terms of their phenomenology. The first thing, as you very thankfully pointed out, is the masses of these two particles. So, in the case of the QCD axion, because you require this particle to actually solve a particular problem of your theory, it has to be related to the fundamental aspects of said theory. And indeed, there is a relation between the axion mass, its decay constant, and the QCD scale, which is roughly this one here. So the axion mass times its decay constant should be roughly lambda QCD squared, or thereabouts, up to order 1 factors. In the case of axion-like particles, on the other hand, you just introduce a mass term in your Lagrangian by hand, and this mass can be pretty much whatever you want it to be. Of course, that is in the sort of bottom-up approach to axion-like particles. If you were to take a stringy approach to axion-like particles, there are sort of ranges of masses that one might expect and not expect. But in general, if I'm talking about Alps, I will consider the mass to be whatever I want it to be. The other difference is in their couplings to photons. And so this is the point where I will start to move on towards the discussion of how you actually detect axions. So the first thing is that the QCD axion has couplings to gluons. It also has couplings to photons, and it also has couplings to other standard model particles. Axion-like particles, on the other hand, can have couplings to whatever I want them to have. The only requirement is that they should obey the symmetries of this particle. So, given that it's a shift symmetric parity odd scalar, it should have derivative couplings to standard model fields that should obey the CP properties of the axion field.
Sorry, for this axion-like particle,
yeah,
they all be CP odd or they can be CP even?
An axion-like particle I would define to always be parity odd.
Maybe just maybe this far from your talk, but I'm trying to think that is there any argument why this string theory always gives CP odd scalar, not CP even?
Yeah. So in the string compactification origin of axion-like particles, it's accompanying a modulus field.
Okay.
Right? So every modulus has a complex partner, which is the axion field, and that one is odd under CP.
Okay.
So in that case, they're always parity odd scalars as opposed to parity even.
Okay.
But the main coupling which people use when looking for axions and axion-like particles is the coupling to photons. So, like I said, this brings me on to how we actually go about detecting such particles. So let's take a little bit of time to discuss axions coupling to photons. So in the case of the QCD axion, the Lagrangian for the axion coupling to photons, and well, in general actually, it'll just be written in this way. So I'll define the coupling to photons GA gamma gamma, the axion field, and FF dual. So in the case of the QCD axion, this GA gamma gamma is predicted to have a very particular structure due to the fact that it actually has some physical meaning with respect to your QCD part of your theory. And this is roughly the fine structure constant of QED over 2 pi, 1 over the axion decay constant FA, and then 2 terms here. So this term is the one that is irreducible. This comes from the fact that your QCD axion, by virtue of coupling to GG dual, inevitably has some mixing with the low energy pseudo-Nambu Goldstones of that theory of QCD. And so it inherits a coupling to photons which you cannot remove due to mixing with the pion. It also has this term here, which is proportional to the QED anomaly coefficient and the QCD anomaly coefficient. So the coupling to GG dual can be preceded by some term n, which is the QCD anomaly coefficient. And I can also introduce, just by hand, this coupling where this would no longer be GA gamma gamma, but rather some generalized G with a QED anomaly by virtue of whatever ultraviolet completion I have for my axion coupling to photons. And so indeed, in the case of the two most common models for QCD axions, the KSVZ and the DFSZ models, I have two different predictions for what this ratio of E over N should be. And this will appear later on in my plots, and so I will explain what they are here. So in KSVZ, you either have 0 or 2 in typical models, and this depends on whether you have charges for your vector-like quarks, which couple your axion to photons, or if they have charges under QED, these vector-like quarks, then you have a E over N ratio, which is 2. In the DFSZ model, on the other hand, this ratio E over N is always 8/3. And so you can see that if your E over N coefficient is roughly 2, then your axion coupling to photons is somewhat suppressed with respect to whether it's 0. In the case, on the other hand, of generalized ALPS, I'm just going to say that my GA gamma gamma is roughly alpha over 2 pi times the axion decay constant. Right, so here, because it's something that I've introduced by hand, it plays no role in solving the strong CP problem, my coupling is related to this decay constant, which I have chosen, but other than that, it bears no relation to pions or to these anomaly coefficients in the same exact way. Are there any questions thus far? Okay. So this is, of course, the coupling to photons, which we are going to make use of in basically all axion detection strategies, bar maybe a couple. And it's certainly the coupling that I'm going to be discussing today with regards to our new detection strategy which we are proposing. So the first thing to note is that this coupling that I've written at the top here can also be written in terms of classical electromagnetic fields in the following way. Okay, so your Lagrangian now has an axion field which couples to the dot product of an E field and a B field. And you can understand this from the fact that the axion is CP odd, and therefore it can convert a B field into an E field or vice versa, but it will not couple magnetic fields to other magnetic fields or E fields into other E fields. And so from this, maybe I should write down with the coupling, from this Lagrangian we can go away and rediscover Maxwell's equations of axion electrodynamics. And indeed what we would find is that now what we remember for the first law of electrodynamics gets modified to include a piece that depends on the axion, and also our second most beloved equation of electrodynamics also gets modified. Okay, so you will recognize the usual, if I have charged sources in my theory, then I'm going to source electric fields. But also now you see that if I have a spatially varying axion field coupling to a local magnetic field, I will also source electric fields. Additionally, you have as sources of magnetic fields not only time-varying electric fields and currents of regular electromagnetic charges, but now also you have this additional term involving both spatial gradients of the axion field, but crucially time variation of the axion field. So if you have an axion which is oscillating as a function of time, you are going to source magnetic fields, or indeed electric fields. And this is exactly the source term that we're going to make use of for detecting axions. And so what we're going to do is that, given that we're going to require throughout this talk that the axion makes up all of dark matter, that the spatial gradients are going to be relatively small, because you should recall that the velocity of dark matter is roughly 1 part in 10 to the 3 of the speed of light. And therefore, anything that has a hidden factor of the speed of light in it is 1,000 times larger than anything that has a factor of velocity in it. And so I'm going to neglect the terms that do not involve time variation of the axion field for now. And so what I'm going to do is I'm going to treat my problem as being one of, I have a new axion effective current that is roughly Ga gamma gamma, the coupling of axions to photons, times the magnetic field times a time variation of the axion field itself. Okay, so how is this useful for detecting axions? Just erase this here before continuing to explain the story. So the main point is that the axion field, if it's oscillating as a function of time, will act as a current. And indeed, what we have is that the axion field as a function of time, if it makes up all of the dark matter, is roughly 2 times the energy density of dark matter, square rooted, over the mass times a cosine. So it is oscillating as a function of time at a frequency set by its mass. And now, this is a sim equal because it's not exactly this expression here, and instead there's all sorts of velocity dependence that I've omitted. But for all intents and purposes, this expression here will be enough for our analysis. And so if you consider this time variation of the axion field, and you consider this form of the effective current, you see, of course, that I can also write my effective current as being sourced by dark matter and being roughly the following, where I'm now omitting the axion phase, because if I look at the experiment for long enough, it becomes irrelevant, and I'm omitting other order 1 factors. And so you can think of it as basically a dark matter source of electromagnetic fields in the presence of a magnetic field. And now you will notice that in preparation for what comes next, I'm already putting in a time variation of my background magnetic field there to sort of get you mentally primed for where I'm going to go with this. So, we're of course familiar with the idea that currents source magnetic fields, and that up to other factors, my axion-induced magnetic field will be proportional to the effective current that is sourcing it. And we're also familiar with what the time variation of magnetic fields will do, which is they will source an electromotive force. And this electromotive force goes roughly like the volume of whatever region in space you're looking in to the 2/3 power times the time variation of your axion-induced magnetic field. Okay. So if
so why is it? What's the power 2/3 come from?
Sorry?
The power 2/3.
Oh, so this is just radius squared, right?
Okay, sure.
So it's the derivative with respect to time of the flux, right, through an area. So it's just area times dA. But I'm writing everything in terms of volume because eventually that makes my life simpler for showing sort of general scaling rules for the various different approaches.
Okay.
So, as we all know, a voltage or electromotive force going through a resistor dissipates some power, and that power is going to be our signal power. And so that signal power is going to go like the axion-sourced electromotive force squared over my resistance of whatever resistor I have times a factor here, which basically asks you, is your resonant circuit in which you plan on detecting axion dark matter, does it have a ring-up time that is long or short compared to the coherence time of your axion field? The coherence time of the axion field comes from the fact that this velocity is actually important in the sense that you can think of the axion as having some sort of inherent quality factor, which we'll define as Q axion, which is roughly 1 over the velocity of dark matter squared. Okay? And this just tells you sort of over what time scale does the axion field in space vary significantly so that you're no longer seeing the original axion that you were seeing, but a different axion that you were seeing with a different phase and different velocity slice. Okay, so this signal power can now be written in more human variables, and in particular variables that I will be interested in terms of, for example, the axion-induced magnetic field, in a way that will be much more suggestive of where we're going to go next. So, from the fact that we have EMF squared, and EMF scales like the time variation of BA, it's going to go like whatever signal frequency I have squared times the axion-induced magnetic field also squared times the volume of my detector, whatever it may be, and then times a factor which is now the minimum of my resonator quality factor Q over the signal frequency omega signal, or the term that is effectively the axion coherence time QA over MA. And so you will notice that I've played a few games by replacing the resistance R with the quality factor of the resonator in this second expression here. But henceforth I will drop the discussion of resistors and talk only about these sorts of quantities like quality factor. Now, for those of you who may have forgotten, in a LC resonator or RF cavity, which can be explained as an LC resonator, it's basically a damped harmonic oscillator. And so if you remember your damped harmonic oscillator equation, it has a second order derivative in time, which is what it is, and you have a first order derivative in time piece, which is the damping term, and that has the definition of what the Q factor is. And so you can think of it as, if you do your experiment for a long amount of time, eventually your signal will saturate once you've gone through Q cycles of oscillation at frequency omega signal. Okay, so this is the formula that we will now use to compare different approaches for axion detection in resonant apparatus. So the first thing is, what do people do in traditional haloscopes?
Sorry, what quality factor is 1/V dark matter square?
Sorry?
Why the quality factor is 1/V square?
Why is the quality factor 1/V?
V square.
Oh,
velocity.
here. So the quality factor is really 1 over the RMS value of the velocity of dark matter, right? So if you take your Maxwellian and you compute what the RMS of the velocity distribution is, it's also roughly just 1 over V dark matter squared. But it's basically telling you that over a certain amount of time, controlled by the velocity dispersion, you will eventually encounter a different phase of the axion field, and so you're no longer seeing the original axion that you were sensitive to, but now a different axion that you can be sensitive to. Okay, so in a traditional haloscope, and this term haloscope is a rather neat one for anything that is looking for the halo of dark matter in our galaxy. The strategy so far has been to say that my background magnetic field, B naught of T, which I wrote in my expression for the effective current that is sourcing my electromagnetic field induced by the axion dark matter, is static. So, indeed, there is no time variation of that background magnetic field, and it is just applied over a region in space. And so what this means is that my induced EMF is going to be proportional to the axion mass, right? Just coming from the fact that there's no time variation here, there's only time variation in this term here, so my time derivative of the axion-induced magnetic field will just go like the axion mass itself. So what this means is that if you want to have a resonant detection of dark matter axions, you must ensure that your signal frequency is equal to your axion mass itself. Right? Otherwise, you will not be able to excite a resonator with frequency omega signal from having dark matter oscillating at MA. So what this tells you is that in a resonant cavity a la ADMX, so this is exactly the strategy that the experiment ADMX, which you have most likely heard of, employs, you would find that your signal power goes like the axion mass squared times, and now I'm going to replace the axion-induced magnetic field, right, this guy here, in terms of the effective current, J effective over ma squared times the volume times the minimum of the quality factor of my resonator over ma and the quality factor of my axion field over ma. So this term here just comes from the fact that in a resonant cavity, the signal frequency is related to the volume, right? And in this expression here, what I dropped was just the length scale involved, right? So indeed, this should go like this. Okay, so what this is telling you is that in a traditional haloscope, your cavity has a size which sets its resonant frequency, which also tells you what axion mass you're going to be sensitive to. And you can do little things by introducing rods and so on and so forth to tune the mass a little bit, but you cannot tune a whole lot because you are fixed by this approximate relation here that relates the size of your resonator with your signal frequency. So what this tells you is if you want to go after light axions, you have to be able to build cavities that are sensitive to slower oscillation frequencies. And this is extremely difficult because the smaller your frequency, the much larger your cavity goes. Right? It goes like the cube power of whatever thing you want to do. So if you want to access, let's say, megahertz oscillation frequencies, you have to build a room-sized cavity, which no one is about to do with a high resonant quality factor. And so therefore, it cannot be done. Or at least it won't be done in the near future. And so a solution was devised to go after these lighter dark matter axions, which is still not the one that I'm proposing here, which involves using, instead of a cavity where this relation holds, you use a lumped LC resonator, where now your signal frequency is set by you by choosing what the inductance and what the capacitance is of your resonant detector. And so now, from this expression here, and plugging it into this expression up here, what you find is that your signal power, in the case of an LC resonator, is going to go like the axion mass squared times J effective squared times now volume to the 5/3 power times the usual term here, involving the various coherence times of either the resonator or the axion field. And so what you will notice is that when you reach axion masses whose frequency is no longer related to the volume, you're actually seeing a suppression in the signal power that you're able to extract, because as you go to smaller axion masses, this quantity shrinks, but this quantity does not shrink. And so this is a penalty at small masses. And so this is where the approach that we have suggested comes in to present a different way of detecting axions on the same principles, which does not suffer from this penalty here. And so the idea is to design a cavity which will almost certainly be roughly cylindrical. Whether it's a cylinder or a corrugated cylinder is something to be determined, which has two resonant modes. So if we draw an axis here where this is now frequency, we have one frequency omega 1, another frequency omega 0, which are nearby in this cavity. And we have, let's say, an axion mass oscillation frequency, which is much, much smaller, but where the difference here, omega 1 minus omega 0, is equal to the axion mass. And so now, if you have a background magnetic field, B0 of t, which is actually a function of t, so let's call it B0 cosine omega 0 t, assuming a monochromatic background magnetic field, then in the presence of dark matter axions, our effective current now has two time-varying components, and so our induced EMF is actually going to go like omega 1 squared, because if you have something oscillating at omega naught and oscillating at MA, you get signal at omega naught plus or minus MA. I'm going to take the plus component because larger is going to be better. So what you'll find is that your signal power now goes like omega 1, our signal frequency squared, times the effective current squared over omega 1 squared, times the volume, times this usual minimum factor, except now, of course, in this part of the minimum, it's Q resonator over omega 1, because remember, it should go like 1 over the signal frequency, and the other one is the same, it's just the axion coherence time there. So if we were to compare these three different expressions, you will notice something, which is that as you go to smaller and smaller masses, this term doesn't change with respect to ADMX or traditional haloscopes, but this term does. Right? There is a slight difference here. And certainly between this expression for this frequency conversion approach and the LC resonator approach, you see that there's a ratio of the signal frequency omega 1 squared over MA squared, which is going to appear. And so indeed, this will allow, in principle, to have a relative gain in this sort of approach, where you have a background magnetic field that is oscillating, as opposed to a lumped LC resonator for small axion masses. Now, there is a caveat to this, which is one that I will explain in just a couple of moments. But this can be overcome by using superconducting RF cavities. So, superconducting RF cavities. So these have quality factors which are routinely greater than or equal to 10 to the 10. So you can think of this as you can oscillate 10 to the 10 cycles before you saturate your signal. And they are generally operated at very, very small temperatures. Okay, so let's do a quick comparison of what our signal powers look like in the approaches that are suitable for low mass axions to see exactly what the apples to apples comparison is for the signals. So the signal powers themselves, or rather the SNR. So the SNR signal to noise ratio in the approach that we're proposing here versus the signal to noise ratio in the LC resonator approach goes like omega 1 over MA times, and now I'm switching notation to Q intrinsic for my my cylindrical cavity here rather than just Q resonator, because this will become important later on, the 1/2 power and then finally a ratio of magnetic field squares. Okay, so this is here an expression where I'm assuming that I'm going to be thermal noise dominated, meaning that the main source of noise for my experiment will just be thermal occupation of photons inside my cavity, which have some spread of oscillation frequencies, some of which will be found at the oscillation frequency of my signal, and therefore will always be present in my cavity as long as it's not at 0 temperature. So the first thing you notice is that my SNR versus the SNR in the case of a lumped LC resonator, as long as the oscillation frequency of the RF cavity is large with respect to the axion mass, is a win. So that gets a big smiley face there. If we compare the quality factors that can be achieved in superconducting RF cavities versus lumped LC resonators, here we're looking at QLC at most 10 to the 8, but typically it's closer to 10 to the 6. And so, again, we get a big smiley face here, because if we're comparing 10 to the 6, for example, with 10 to the 10, then I get a factor of 100 enhancement of my SNR here. For the comparison of temperatures in the two approaches, it's a little bit more iffy, because in principle, the LC resonator can be cooled to very low temperatures, and it can probably be cooled to lower temperatures than the RF cavity, because you don't have a honking big source of power being dissipated very nearby. But nevertheless, you do have to cool it down, and so this is sort of not clear whether it's a loss for us with respect to an LC resonator, but very likely it is a small loss. The place where the LC resonator certainly compares favorably is in the fact that you can apply much larger static magnetic fields than you can support oscillating magnetic fields. And indeed, the typical sort of comparison to make here is that the peak magnetic field that you can support oscillating is about 200 millitesla, versus the peak magnetic field envisaged for these sorts of static background magnetic field experiments is more like 5 Tesla. And so this gets a big fat frowny face. Yes?
I feel I should be able to do this for myself, but I'm going to ask you.
Yep.
So this statement over on the right that omega signal goes as the size,
Yeah.
has a nice solid visceral feeling to it.
Yeah.
And what's happened to that on the left?
Oh, so
how are you arranging this so the
it's still
you
here.
get the
So
difference
this,
without building a huge thing or whatever?
right. So the point is that in this approach, you have two frequencies which are nearby, which are both related to the volume of your cavity. Right. One will be for a particular type of mode, and I'll explain that in just a moment exactly how this works.
Okay, so
the other one will be a different mode, but they will both be modes where omega 0 and 1 are roughly like sort of like the radius of the 1 over the radius of the cavity. But the separation of the two is the thing that you, in principle, as the experimentalist, can tune to match the axion mass, which can then be much, much smaller.
So it's just that that statement is way too simplistic.
No. This statement is correct.
But
this statement is also correct.
But it's just that you can tune into the differences.
I want to tune into the difference of the two frequencies.
And that's something you can do.
Exactly. But in order to do that, you need to have an oscillating background magnetic field. You can't do it with a static.
Good.
Yes. So, of course, in any of these experiments, a major issue to be discussed is how you scan axion masses. So I sort of briefly alluded to the fact that in this experiment you can insert tuning rods to slightly change the frequency by changing the geometry. In this experiment, it's pretty clear you can just change your capacitance or your inductance and therefore change the oscillating frequency. In this type of approach, you have to do something a little bit different. And so here it's worth mentioning that in a cylindrical cavity, what are supported are transverse electric modes with different labels according to azimuthal, radial, and longitudinal variations of their fields, and transverse magnetic fields, which, as you can imagine, are sort of the conjugates of transverse electric field. So transverse electric just means that there is no longitudinal electric field component, and conversely for TM, no longitudinal magnetic field component. And so axions, given that they are parity-odd scalar fields, have particular transitions that are allowed. So the first thing is that the azimuthal component has to be the same in the two modes that you want to have transitions occur between, because it's a scalar field, so it cannot change the spin of the field that you're looking for. The second thing is that the longitudinal component of the two fields should not be equal, because it's a parity-odd scalar field, and so therefore you want to convert E fields into B fields in the same, pointed in the same direction, right? You recall the Lagrangian had a term that looked like A E dot B, right? So I'm converting between parallel E and B fields. And so what this tells you is that TE to TM transitions are allowed, and TE to TE transitions are allowed, but to TM to TM transitions are not allowed. But the key thing that you want to obtain is near degeneracy in order to access small axion masses between the signal frequency omega-1 and the background frequency omega-0. And this you can obtain by looking at the longitudinal and radial dependence of your TE and TM modes. And what you find is that as a function of the length of your cavity and its radius, you have solutions where the two frequencies are exactly degenerate to this equation here involving the indices and the zeros of the field. So here I'm doing TE to TM transitions. These are the longitudinal indices P1 and P0. These quantities xmn and x'mn are the zeros of the Bessel function. So this is a zero of the regular Bessel function mn, and this is a zero of the derivative, the radial derivative of the Bessel function mn1. Okay, if I were doing TE to TE transitions, it would just be x prime mn0 minus x prime mn0, mn1. And so if you find a solution for degeneracy, then you can also find solutions where they're almost degenerate but not exactly degenerate. And you can see that what you should do is you should tune the ratio of the length to the radius. So in a typical cylinder, we're not going to want to change the radius because that's going to be relatively difficult. But instead, what you're going to want to do is change the length. And so scanning here can be done by changing the length of this cavity so that the two modes see effectively two different lengths. One obvious way you can think about doing this is having your background mode be insensitive to the length. So let's say P0 is 0 and P1 is non-zero. Then as you change the length, all you're changing is frequency omega-1, but you're not changing frequency omega-0. So the length can be changed in two different ways that we have thought of so far. The first thing is just to exert pressure with piezoelectric actuators. And so if you use piezos, you can have tuning. So now I'm looking at changes in the frequency. Just erase this here. Changes of the frequency that go maybe up to a megahertz. This comes from the fact that over a meter-long cavity, piezoelectric actuators can maybe deform the cavity by about 1 millimeter. 1 millimeter in a meter-long gigahertz cavity is roughly a megahertz. The other thing one might be able to do is introduce some sort of mechanical plunger, which you then move up and down with much larger changes in the length of the cavity. And so if you have a plunger, your delta omega would be less than or equal to whatever you can do that doesn't completely screw up the properties of your cavity. So let's hopefully say that this can allow us to scan of order 100 megahertz. But it remains to be seen whether this can be achieved while maintaining the high quality factor of the cavity. Okay, so that was the detour into scanning. So let me sort of discuss a little bit some of the other pertinent issues, and for this I'm going to want to use the screen.
Question?
Yes.
That top equation, maybe you're going to get to this.
Yes.
It's very nice to have a ratio of signal ratios.
Yeah.
But in fact, in the end, of course, we're interested in the actual signal-noise ratio of the experiment.
Yes.
For some period of time, and maybe you're going to get to that.
I will get to that, yes. Yes. But I will get to that in our approach only. Okay. So this is just the pretty picture of the cavity with all of the things that I just told you. Now, let me show you some expressions for the signal. So the first thing to notice here is that I have, so now I'm going to do everything in terms of power spectral densities. So this is sort of the amount of power per unit bandwidth that your experiment would see. And so what you see here is that your signal power spectral density goes like the coupling squared and the background field squared, exactly as I promised earlier. It also has this other parameter, eta10. So this eta10 parameter, which I want to cover this, is basically telling you how much does your signal field overlap spatially in the cavity with your background field. So eta10 is going to be proportional to the volume integral of B naught dot E1. Okay, and then here, this is just the fact that a resonant cavity has some sort of transfer function, and this transfer function follows sort of a Bright-Wigner shape. And this part here is telling you that your axion has some frequency dependence itself. This comes from the fact that the axion is spread out in velocity space, and therefore also spread out in frequency space. And so it has its own inherent axion power spectral density, which is defined by requiring that the time average of the axion field squared gives you the relic abundance of dark matter. This is the power spectral density of your background magnetic field itself. So if you have a monochromatic loader, you can go away and calculate exactly what your signal power will be. You will find that it's given by this expression down here below. But in general, it could be something more complicated. So if, for example, you could have a flat top which then has some decay either side, or it could be a much narrower flat top with some decay either side. And indeed, these tails of your loader are going to become important in just a moment when I discuss some of the noise issues in this experiment. So some things to note, of course, are that you want to try and maximize this overlap parameter. So in these cylindrical modes that I was discussing here, you might have overlap parameters that are normalized such that this eta10 is about 0.5. A way to improve this overlap parameter is to use corrugated cylinders. So this would be like thinking of two concentric cylinders where they have a semi-permeable membrane around the outside. And you can also have corrugations on the ends so that the two modes see different lengths of the cavity. And so that would be another way to have some sort of tuning that's sort of like a plunger. And in those sorts of corrugated cylinders, this overlap parameter might be about 0.8 as opposed to 0.5. The other thing is that in this calculation here, we're using a standard Maxwellian velocity distribution for the axion field, as opposed to some sort of block approximation. But of course, as has already been pointed out, we'd like to see an SNR, and so in order to obtain an SNR, we need to know what is the noise in our experiment. And so let's first consider the standard noise sources in our experiment. Is there any way to get this a little bit lower?
Lower? Pull.
Yeah.
And
Stay? Okay, that's nice. Perfect. So, in the case where you have just a cavity at some temperature T, you inevitably have thermal noise in your cavity. But of course now that thermal noise, which is here referred to as 4 pi T, is getting filtered by the usual transfer function of your cavity. And then there's an additional factor here that comes from how you actually couple to the readout of your cavity. So it would just be this part of the expression for the power spectral density of thermal noise if I had no holes coupling to my cavity whatsoever. But of course, in a realistic experiment, that cannot be achieved. And so instead, what you have is the following relation, which I will also endeavor to leave up here, which is that basically quality factors add like resistances in a series circuit. So 1 over the quality factor of your signal mode Q1 is like 1 over the intrinsic quality factor of your cavity, or your unloaded quality factor, plus 1 over the quality factor of whatever you're doing in order to couple to that cavity to be able to read it out at all. And so as we will see later on, I'm going to actually want Q1 and Q couple to be close to each other, and Qin to actually be a little bit higher than both. And this is because there are additional sources of noise beyond just thermal noise. But also in the case of thermal noise, you would certainly want to overcouple in order to maximize your signal-to-noise ratio. So in practice, the temperature at which we would plan to operate would be below the superfluid helium transition. So this is sort of like 1.8 Kelvin. But because of the nature of this proposed experiment, you also have non-standard sources of noise. And so in particular, the fact that you have an oscillating background magnetic field means that you have what's called phase noise. So this comes from the fact that as you inject power, you might accidentally couple to your signal mode at the loading point, or you might accidentally couple to your loaded mode, your background mode, at readout. And so if you have a misalignment between the fields at loading and at readout, parameterized by this parameter epsilon 1d, which you should think of as the volume integral of E1.E driver or E1.E readout, or E0.E readout at the input and output ports of the cavity. If your loader actually has support beyond the central frequency omega naught of your resonator, so that's what's parameterized here, so this is the phase noise. Basically your driving voltage has some variation, some wiggle, so that it actually provides power at frequencies that are not your central frequency. Then, as usual, filtered by the transfer function of the cavity, you're going to have phase noise. And this comes from this power spectral density of the phase noise of your oscillator, whatever that may be. And so in practice, what we did is we looked at commercially available master oscillators, and they produce very nice phase noise curves, which you can digitize, and you can extract what the power spectral density of the phase is, and therefore estimate at least sort of what the phase noise would look like in a realistic experiment. And so this power spectral density of the phase has bits that are flat, so frequency independent. It has 1 over frequency components, and it also has 1 over frequency squared and 1 over frequency cubed components. So as you can imagine, as you go to lower and lower separations between the two frequencies, when you're nearer and nearer the peak, this guy is going to become rather important. The second interesting source of noise is vibrations in the walls of the cavity. And I would actually argue that this is a source of noise for all experiments. They just haven't necessarily considered them in the other ones. Here it's particularly noxious because, again, you have a lot of power stored inside your cavity, and so your mechanical noise is therefore much bigger than in other types of experiments. But this basically just comes from the fact that if you have a photon that interacts with your wall that is vibrating at some mechanical resonant frequency, then again, the same process can occur with the axion. You can upconvert into a higher frequency photon through that vibration with the wall. And so the way you parameterize this is by looking at the power spectral density of displacements of the wall. So you look at how much does the wall actually move if you apply some external force which has its own power spectral density there. And if you are unfortunate and you have a situation where your frequency is exactly degenerate with a mechanical resonant frequency, then this gets maximally enhanced. So you can see here, this is again going to be dependent on how well can you couple to the loaded mode versus the readout mode, because this does not have the same property as the axion field, where it doesn't change the parity of the field inside the cavity. It's just sort of spreading the frequency of the background oscillating mode. And so, again, you just want to be able to isolate the readout of the background mode as well as you possibly can with this rejection factor epsilon 1d. And you can see that you're going to have some filtering by cavity Lorentzians, which is a little bit more complicated, and if people have questions about how that arises, I would be happy to explain it. And that's certainly a new noise source which others have not necessarily considered in the past. Then another noise source, which is novel to this particular approach, is one that people who are familiar with accelerating RF cavities are also very familiar with, which is that of field emission. So this comes from the fact that when you design a cavity, whether it's for accelerating or for anything else, you have electric fields inside your cavity. Your cavity is also not perfect. It's not smooth everywhere on the interior, and indeed you have lots of places where there are imperfections on the cavity surface. And as we know, if you have an imperfection, then the gradient of the potential is much larger at a point than it is on a smooth region, and so your electric field is actually enhanced near that imperfection, and it can be enhanced sufficiently large so that electrons can be shed off of those imperfections and get dumped into the cavity. When they get dumped into the cavity, they get accelerated because there's an accelerating gradient in that field. And so those accelerating electrons, as we know, will emit radiation. So they emit radiation in three different ways: synchrotron, transition, and Bremsstrahlung radiation. So synchrotron radiation comes from the fact that an accelerating particle going through some region is radiating off photons, right? This is typical radiation. Transition radiation occurs because as it encounters the wall of the cavity, it goes from a region of one dielectric constant to a region of a different dielectric constant. And therefore you have transition radiation from encountering that barrier. And finally you also have Bremsstrahlung radiation, which is where most of the energy of that electron is lost once it gets sort of absorbed into the wall and it dissipates all of its energy in the form of heat. All of these different types of radiation actually have sort of different bandwidths over which they're emitted. And so when you actually compute the power spectral density normalized to the on-peak thermal power spectral density, you find that as long as the total power lost to field emission can be limited to 0.1 watts, bearing in mind that the whole cavity power is of order 100 to 1,000 watts, then the power spectral density of synchrotron radiation is the same as the power spectral density of thermal noise, and the transition and Bremsstrahlung radiation power spectral densities are much, much smaller. But this is a big unknown, which is, can you actually limit the total power loss to field emission to below or equal to 0.1 watts? For reference, RF cavities for acceleration, when they're designed, have issues with field emission, and if the field emission power loss is greater than 10 watts, then the cavity is just thrown out. It's considered a failure. But of course 10 watts and 0.1 watts are quite different. And they just don't measure below 10 watts, so we don't know whether 0.1 watts is a reasonable number or not until we go out and actually measure it. Okay, and since I am running out of time, let's just quickly show you what all of these noise sources look together on a pretty picture, but more importantly, what they look like in terms of the relative noise power of these different noise sources. So here I'm showing you a plot for a geometric rejection factor of 1 part in 10 to the 7, and an intrinsic quality factor of my cavity of 10 to the 12. And you can see now, here this is plotted as a function of the axion mass, which you can also think of as the frequency separation between the two modes, the background oscillating mode and the signal quiet mode. What you see is that for these parameters, thermal noise dominates almost everywhere. There's also quantum limited amplifier noise, which is always there, but assumed to be smaller. And then you see this big jump where mechanical noise suddenly becomes an issue, and I'll explain that in just a second. And you have the phase noise, which becomes ever more important as you get closer to the carrier frequency. So the feature that is shown in this mechanical power here is actually rather interesting. And it comes from the fact that your mechanical noise is enhanced if you're near a mechanical resonance. So if your axion mass that you want to measure is degenerate with a mechanical resonance, then you're going to be maximally overlapping between the mechanical noise and your signal, and so your mechanical power is going to be maximized. And so it has this rather curiously large growth as you go to smaller and smaller frequencies. And this is assuming that for every axion mass there is a degenerate mechanical resonant frequency. However, these mechanical resonant frequencies don't go down to arbitrarily low frequencies. Indeed, they end at a certain point. And so in fact there was a group of Italians who were planning on using superconducting RF cavities to measure gravitational waves, which went out and measured in a prototype cavity at CERN the forest of mechanical resonances. And they found that the lowest one was at roughly kilohertz frequencies. And so we assumed that for this plot, that the mechanical resonances end at about a kilohertz, and that, as you might expect, the sort of wall displacement is maximized by the lowest lying mechanical resonance. But then it just ends, and then you're off resonance, and so you have this standard 1 over frequency squared dependence at even lower frequencies. If there are any questions about that, I would also be happy to explain those offline. So finally, let me show you some plots of the sensitivity of this approach. So here I am showing as a function of the axion mass and the coupling to photons along this side, and just to guide the eye, for those of you who are more sort of model building inclined, also the axion decay constant on the right hand side. The yellow band tells you where the axion would solve the QCD problem, strong CP problem that I explained at the beginning, and this red band is where the misalignment mechanism for an order 1 misalignment angle gives you the correct relic abundance of an axion-like particle. This intersection of the two lines should not be taken to mean that ADMX has been looking in the wrong place for QCD axion dark matter. It is looking in the correct place. It's just that if you take the QCD axion, there are additional complications to how the dark matter abundance is obtained that actually push up where this band would live to actually somewhere around here for a QCD axion. Okay, so this should not be taken to mean that there's anything funny going on there. But let me explain to you quickly what the sort of general dependencies are here. So as you can see, there's a sort of roughly m to the 1/2 scaling at high axion masses. And this is the case when you are thermal noise limited. So here, to guide the eye, there's a continuation of the line if I were to remain thermal noise limited throughout. But you will recall from the previous slide that at some point other sources of noise take over from thermal noise. And indeed, in the intrinsic quality factor of 10 to the 10 and geometric rejection factor of 10 to the -5 line, you can see that there's a point where the mechanical noise starts to dominate, and it's evidenced by this sharp, fin-like structure in the reach curve. But then once you go below the lowest line, mechanical resonance, and where exactly this feature would be would depend on the actual cavity you build, you start to become dominated by a combination of mechanical resonant noise and phase noise, and so you have this 1 over f squared decrease in your reach. For the intrinsic quality factor that's higher and a geometric rejection factor that's higher, obviously the effects of these noise sources are mitigated further, and so you have higher reach than you would in the other case. So it's worth just going through that in a little bit more detail to show what are the different parameters that affect your reach in different cases. So here I am fixing the geometric rejection factor, I am fixing the maximum displacement of my cavity walls, and I'm fixing the integration time to be of order a bit less than a year, so about 1/3 of a year. And here I'm just varying the intrinsic quality factor. And you see that at high masses this has a sort of almost linear impact, but at low masses this impact is exacerbated by the fact that obviously your phase noise and your mechanical resonant noise gets worse if you have a lower intrinsic quality factor.
Question.
Yes?
So if you integrate for up to a year, you have to do that at every frequency.
Yes.
And therefore and you don't know what frequency you look at.
Right.
So there is an efficiency loss.
Yes.
That's given by the scanning time required, which is like 1 over the half power.
Yeah, so that's been baked in here. So
Okay.
I've set the integration time per e-fold. And so then I'm just saying that for a particular e-fold in axion mass, I'm going to set for that amount of time, and then you go through the whole thing. Yeah. So the whole thing takes of order 10 years.
Okay.
here, this plot shows you what the impact of that geometric rejection factor is. So in the most aggressive line where I have a geometric rejection factor of 1 part in 10 to the 7, which in terms of sort of meaningful units, you should think of this as sort of nanometer control of the geometrics of your cavity. If you have 10 to the minus 5, you have this line where at high axion masses, since you're not mechanical nor phase noise limited, it has a marginal impact. But eventually, as you get to too large a geometric lack of control, then you start to lose in terms of the reach even at high axion masses. But you can see that even for sort of order hundreds of micron level control of your cavity, you still have pretty decent reach at high axion masses and a non-trivial reach at low axion masses. So it's certainly not the case that you need to go to nanometer control of the cavity walls in order to achieve interesting reach. And also it's worth bearing in mind that before I was showing plots where I was assuming that the wall displacement was never greater than 0.1 nanometers, which for reference has been achieved in a SRF cavity at Fermilab, which is being used for other purposes. But if that minimum wall displacement were greater, so here I have the reference curve of 0.1 nanometers, but also curves of 10 nanometers, 1 micron, and 100 microns, you see that this also affects your reach. And interestingly, it means that your reach is cut off at higher and higher axion masses. And this just comes from the fact that if your walls are moving around, not only are you spreading noise around, but also your resonant frequency is moving. And so you don't know where it is anymore. And so there comes a point where you just don't know that you're in the bandwidth of your resonator at all. And so you don't know whether you're actually exciting the signal mode or not, if your cavity is sort of vibrating too much. Finally, if you're impatient and you want to spend less time per axion mass, this is a plot showing you how the reach changes as a function of changing the e-fold time for each e-fold in axion mass from 10 to the 7 seconds to 10 to the 5 seconds, 5 10 to the 3 seconds, and 10 to the 2 seconds. And I realize now, of course, that having said all this, I never actually presented you with an Snr equation. The reason is actually quite simple. Only when you're thermal noise limited can you really give a nice Snr expression, because there it's relatively straightforward. Down here, where there's all sorts of different noise sources which are comparable in size, it's much more complicated. So in general, the way we compute the SNR is by saying that the SNR squared is the integration time times the integral from 0 to infinity over the frequency of the power spectral density of signal as a function of frequency over the power spectral density of noise as a function of frequency squared. And so this is what you use to then extract what the signal to noise ratio everywhere along here. So I'm afraid that's a little bit over time, so I will stop here, but there's a lot of other things that I could say, so if you have questions, please feel free to ask me. Thank you.
In your plot, you always assume the dark matter, it's all on the dark matter.
Yes.
So that if you are off this band, which means your theta is to be deviate from 1, right?
Yeah. So if I'm thinking of Alp dark matter, then I can just think about varying theta to get Alp dark matter somewhere else on this plot.
Yeah, so it's theta bigger than 1 in the upper,
let's see, theta bigger than 1.
You move up, or?
Theta bigger than 1 is going.
Theta, I think theta is larger, which means f is small, right? No, but this does not solve the structural problem.
No, but just for Alp dark matter, right? So you want theta, yes, you want theta FA to stay constant, so bigger theta is going up this way.
Yeah, so there's some limit, right, at some point.
Yeah, absolutely. And so then, if you want to talk about out dark matter, like let's say up here, it's not misalignment, right? It's going to be something else entirely. But I mean, to do an apples-to-apples comparison with other axion dark matter experiments, it doesn't make sense to say, well, we don't know what dark matter could be up here, right? So you just want to say, if there is axion dark matter up there, then this would probe it, regardless of what the origin of that dark matter might be. Yeah.
In my experience, it's really easy to kill the Q of a superconducting cavity.
Yes.
And one way to do it is to try to inject power from some kind of source into it.
Yeah.
And so you look up the phase noise, but then there's the impedance matching and the coupling and the resistive component of noise for the oscillation.
Yeah.
And then you mentioned briefly the amplifier. All those things kill the Q.
Yeah, so the loaded quality factor of the cavity is like 10 to the 9 or so. Right.
That's achievable in principle, but then you have to have a quantum limited preamp, which is no feet.
Right.
And you have to have a very weak coupling to the oscillator.
Yeah.
Really, minus, I don't know, 20%. But it's sort of like LIGO. You just feed a lot of energy into the cavity.
Yeah.
And then you look for the signal.
Yeah, what's the difference?
It's sort of like, it's really like LIGO.
Yeah, and in fact, so the origin of this idea was from studying this Italian paper that was trying to use SRF cavities for gravity waves, where they were using a similar approach, right? Frequency upconversion to look for gravitational waves, where instead of having axions in the cavity, you would have two coupled cavities such that you have sort of parallel and anti-parallel modes in the coupled cavity setup. And you would have a relative quadrupole between the two cavities, such that the gravity wave would interact with it. And there, you can think of it in two ways. The gravity wave is either interacting with the quadrupole of the electromagnetic fields, or it's interacting directly with the walls of the cavity. But there, of course, your wall displacement is both your signal and your noise, and so it suffered greatly from that. It turns out the reach of that is not very interesting. But yeah, this is a lot of the literature on this, particularly on mechanical noise, was something we also found in sort of gravity wave literature.
Seems like there's a great field to be gained by building not just one, but start building and you keep building.
Yeah, so that's certainly true in most of these axion dark matter experiments, right, where you want to build as many as you possibly can afford to look at different axion masses, yeah. Because the
10 years is too long.
Yeah, the scanning with the plunger is also particularly scary to us because this introduces new regions where you might have impurities, especially along the edge of the cavity, and also you're trying to move something inside a very finely balanced cavity, and you would certainly affect the quality factor of the cavity if you have something that's movable at one end of your cavity. The piezos are a little bit more achievable in that sense, but of course your scanning range is not so great. And so sure, you can scan from here to here in one cavity, but if you want to go from here to here, you need 100 cavities, and that's not great. And so there are certainly lots of technical issues to be addressed. And so the current status is that we have a small corrugated cylinder cavity at SLAC that Sami Tantawi, one of the authors, had on hand, and we're just looking to see sort of how cross-polarized can you get these fields, just to see what are the geometric rejection factors one might achieve in such a cavity. But in the end, a purpose-built cavity will have to be manufactured because, for example, that one is a conventional RF, it's not SRF, and so on and so forth.
I imagine the Q's not 10 to the 12th either.
No.
Corrugated.
The corrugated conventional RF cavity has a Q factor of like 10 to the 5 or something, Q to the 5. But yes, there's also the SRF group at Fermilab and an SRF group at CERN that are interested in trying to see if they can solve some of the technical issues behind the approach. But obviously the trade-off is if you can achieve it, then there's some interesting regions to be probed.
It's a fun experiment.
Yeah.
We're doing something similar here. You've probably heard Anyways, I don't know where far. It's a variant of Ken Durwin's experiment, but electric instead of magnetic. But it covers that same region you're talking about.
Yeah.
So the vertical, the y-axis is basically the coupling constant. The coupling between a hidden photon and Maxwell.
Right.
So it's analogous to what we had on your y-axis.
Yeah. Yeah.
Yeah, that's the coupling.
This one. Sorry. Yeah. This one.
Keep us off the streets, that's for sure.
Yeah.
So, another question? So, let's thank speaker again. Sebastian, this resonant cavity, same as EMS?
No, these are like HF.
Okay, I see this.
There's
That's
another
good.
one called there's a few resonant cavities up here, but they haven't achieved quantum limited readouts. The only one that has is ADMX and then Haystack, which is this.
Haystack.
Haystack. Sorry?
We should do a state will make sure.
Oh, I don't know about Haystack.
Might actually do something like that.
It's okay. So, but you mean this one has no result yet, right?
How I adjust.
No, these are all limits. These gray regions are all already excluded.
Ah, no. But I thought
This is not showing projection, so there's something rather interesting about the axion dark matter literature, which is that proposals never show the comparisons with other proposals reached.
Yeah, but LC circuit was reached out.
Oh, I understand. You show
Yeah,
us.
so you only show regions that are excluded, and you don't show what other experiments propose to exclude. So for reference, DM radio, right, which is a lumped LC resonator, can roughly probe to about here, and then it goes horizontally across.
Okay.
Well, actually, there's a bit of an issue. Because DM radio is limited by the size of, as you pointed out.
Yeah, there's a Compton wavelength.
The size actually moves you up like that. Both for
yes.
Kent's experiment and our experiment, we're limited by the size of the cavity or the size of the lumens.
Right, so in Kent's experiment, they actually showed, and they put out like a 180-page paper on optimal electromagnetic.
It's better to read it from the back.
Yeah, where they showed that actually if you overcouple, so if you lower the coupling quality factor, you can make it at worst horizontal for some frequency
range. Yeah,
so and then eventually you get killed by the Compton wavelength.
Yeah, our experiment is the same thing. If you have a moment, I can take you to the third floor. But anyway, sure, actually, we've been running for a year, so yeah. But yeah, it comes down. We go up here like this.
Yeah.
Come down, and then we're flat for a little bit. Down to about here, and then it goes up like that. And it's all hopeless because of the size of our shield.
Right.
Sorry. Sensitivity. And then one of the ideas that somebody had, it might have been Peter Graham, is that if we put a fixed magnet in the room, then we could detect things. That's sort of a cheap shot.
Yeah.
But any fixed magnet that's big enough would do the conversion from axions to
Yeah,
Maxwell.
absolutely. Yeah.
It's a fun experiment. Is LDRD going to pay for this, or how are you going to?
No idea.
Early days.
Yeah, so I think the next step is one of Sammy and his collaborators will probably put in a proposal to SLAC to get some money to at least do some initial R&D. And then I think the group at CERN has somewhat unofficially enabled themselves. So at CERN they have this weird structure where people are required to report what they spend their time thinking about and what they spend their time doing in the RF group.
It's separate.
Yeah, so their main goal is of course RF for the accelerator. And so
unless you think about that a lot, then,
so the guys who are thinking about this have apparently succeeded in convincing their superiors to let them spend some small amount of their time thinking about this and not just RF for accelerators. But I don't know what their status is at the moment.
it's fun. Yeah. Anyway, I can send you. We have a poster, and we're about to publish a paper on our results
Ah, great.
next month. Haven't found anything, but we're down to 10 to the minus 14 and a half down here. All the way up.
Yeah.
It has the advantage that, unlike Kent's experiment where he has to stick at some frequency and let the cavity ring up, and then, so it's one graduate student per factor of 10 in frequency. Our experiment does the entire 1 gigahertz at a time in parallel because of wideband FFT that we have, and looks at the electric field and digitizes the entire spectrum simultaneously, looking for. But it's the electric analog of Kent's magnetic experiment.
Yeah. Right.
Instead of having an LC circuit, we just basically have an antenna that looks at the entire, well, within its bandwidth. You can't design an antenna that will look over an infinite amount of frequency. So we have a series of antennas and amplifiers.
So you're looking for a big electric field.
I'm looking for an electric field. Actually, not a big one. We're measuring femtovolts.
No, I mean big by
big
compared to zero.
Big. Sure.
So if you have 10 minutes, can I show you something different?
Sure.
So